Okay, so this video is on derivative shortcuts, which should sound like just about the best thing in the world right about now, because in reality, doing the derivative, the only way that we really know how to at this point, which is using the definition of the derivative with the f of x plus h, that whole guy, it I mean, it gets the job done. It's correct. It's technically it is the definition. There is no alternate, oh, the definition of the derivative is also blah blah blah. Like, no, that's it. That is the definition. And that is how one needs to, or that's how one computes derivatives, is using that formula. But of course, if there's a way to maybe avoid having to do that every time, and maybe just some sort of shortcuts, and even just some basically a table of derivatives of sort of famous ones, that might be much preferable compared to actually having to use that thing every time. So that is what we will begin in this video. And there's a good I don't know, let's say five rules and about a dozen standard derivatives that together will make basically a chart of all of that. And that's actually really going to be the actual way that you compute derivatives in reality. And by reality, I mean in this class, and if you ever actually needed to do this, this is how you would more so probably do it than with the, with the formal definition with the f of x plus h guy. So this is very good news for us, that there are shortcuts and there are just some basic things that we can memorize in order to be able to do derivatives actually quite quickly. So it's fine to use these shortcuts, for everything. The only stipulation, I guess, or exception that I'll make to that is that I will ask you on the exams to do one, the long way with the definition of the derivative with the f of x plus h, just to have a sense of, well, that's where it comes from, and technically that's where all of the rest of these ones that you're going to be able to do much more quickly all came from someone sitting there, and doing that f of x plus h business with all of these guys and saying, well, here's what I got. And so the shortcuts are what you'll use obviously almost all the time. But don't totally throw away the definition of the derivative, because we'll use that again just a little bit. So anyway, all right. So what are some shortcuts? So just to not completely just present these to you and say, here, memorize these. Let's at least do a little bit of thinking, and say, well, what derivatives do we know so far? And then maybe we'll just sort of use our intuition to make an educated guess as to what a rule might be. So let's see. So what derivatives? So known derivatives that we've sort of computed, I guess, right? That we've computed using the old, using the definition. So I'll just write it up here one more time, right? The real definition of how do I do the derivative is to do this, and then take this quantity on the right here as h goes to 0 or as h equals 0, evaluate what that is, right? That's how you actually do a derivative by definition. So we use this several times to do some derivatives that we already know. So let's see if there's something we can say about them and maybe make a guess as to what a rule might be. So known derivatives, what do we know the derivative of? Well, actually, before we even used this formula, we knew a couple of derivatives just by sort of, inspection, right, or just sort of guessing. So I'm going to just list a few of them for you, or a few things that I think we know that we actually already know how to do the derivative of. So the easiest kind of thing I can think of, the easiest kind of equation or object that I might be, is what if I just have the equation of just a constant, or in other words, do I know what the derivative of just a number is, like 5 or something like that? So if I have just a constant, some number, which we'll usually use k for constant, Do I know what the derivative of that is? Well, I claim that actually we do know what the derivative of just a number, right? So what's the derivative of 4 or something like that? Well, just think for a second. Okay, this isn't actually using the formula over here, but think just for a second. I'll try to connect this here. Well, if I did a graph of a constant, okay, so if I had, for example, f of x, or I'll just say here y equals 2, for example. What is the graph of that? Well, the graph of any y equals a number is just a horizontal line. That's, for example, y equals 2. Okay, so that's fine. Well, we know, right, if you know nothing else, you know the derivative is the slope. Okay, well, what's the slope of a horizontal line? Well, it's flat, isn't it? Right, a horizontal line is just completely flat. And we know what flat means. Flat means that the slope is 0, right? So rise over run. So there's no rise, but there's plenty of run. So there's so the slope is 0, which means if I was to take the derivative of just of an equation, right, that is just a constant, like 2, for example. A constant just means a number. I should get 0. Okay? So this isn't much of a proof, but it's actually, well, actually it's not bad in order to at least justify that if I have just a constant, I think the derivative should be 0. Okay. Well, what's one sort of step harder than a constant? Well, what if you just have x? Okay, so what's the next hardest thing, I guess? Well, not just a number, maybe just, how about just plain old x? Do I know what that is? Well, again, I'm going to appeal to just sort of a quick, brief little graph here. What is the equation, what is the graph of y equals x? Well, that's just a diagonal line, y equals x, because technically it is of the form y equals mx plus b. It's just that m is 1. So let me, give myself some more space here. So y equals x is really y equals 1x plus 0. That's what y equals x is. So if I'm trying to figure out what's the derivative of just plain old x, so I don't know. Well, if I look at the graph of just y equals x, then like just x, I get that. I get just a diagonal line. Well, again, I'll just use my very basic definition of what is the derivative. The derivative is slope. What's the slope of this line? 1. There it is, right? Y equals mx plus b. M is 1. So the derivative of x should just be 1. Okay, well, so far I haven't actually used this big clunky thing up here, right? I haven't used that at all because I've just been able to kind of do a little, I don't know, I've told you a little story, and that's sort of been a demonstration of these derivatives. Well, I'm SOL at this point to keep just telling you little stories because I don't think I know how to do much more that's anything harder than just either a constant or just a line. So I do need to, sort of bring in the big guns, I guess, to say, well, I don't know, what's next in terms of complicated? Well, I don't know, how about x squared, right? I basically did a constant, which doesn't have any x's at all. Then I said, okay, how about if you just have x to the first power? Well, we know that derivative just by graphing should be 1. Okay, well, how about x squared? What happens when I do the derivative of x squared? What do I think that should be? Well, I can't just draw you a little picture and tell you a story and get the answer. But this is one that we've done before. We've done the derivative of x squared, and in fact, we've gotten 2x, I think, when we did that. So we know that one. And actually, I think we did even one more. I think we did x cubed. And we computed that the derivative, I believe, was 3x squared. Okay. So what are we going, so if I want to try to sort of at least just use, I should say, this is about it, right? I don't think we know how to do the derivative of a whole lot else. I mean, we did do some other examples. And I should say, remember, I did use this clunky definition in order to do x squared and x cubed, right? We did those examples if you look back in your notes. And we did a few other examples that were just sort of combinations of powers of x. Okay, so we have done a few other examples, but basically this is about it. We haven't done things like sine of x or e to the x or even x to the fourth power. I don't think we've done. So this is kind of, if we're trying to sort of come up with what do we know so far, this is about it. It's pretty much this chart here. Now I could continue to use the definition of the derivative here, right? And I could use that to, for example, do x to the fourth and x to the fifth and so on. But to be honest, I mean, one could do that, but even for me, that's a 10, 15-minute computation to try to do higher powers of x using that formula, just because it's a bunch of algebra and it's nasty. So that's not great. I don't think I want to do that. And moreover, that doesn't really get me the answer to things that aren't just powers of x. So I want to do a little bit of guessing, I guess, right? Is sort of the idea of saying, well, all right, if I wanted to try to generalize what I see here in my little list here and say, all right, what could I say about just generically, how about just powers of x in general? Well, I have x to the first power, and that turned out to be just 1. I have x squared, and that turned out to be 2x. And then I had x cubed, or x to the 3, and that turned out to be 3x squared. So, you know, I'd sort of ask, if you think about a little bit of a puzzle of just sort of a what's, you know, spot the relationship or spot the pattern. Hopefully one thing jumps out at you pretty strongly, which is that it kind of looks like the exponent here of x, doesn't it kind of look like becomes the coefficient over here, right? I mean, that'd be a pretty striking coincidence if it wasn't actually always the case. And it is. Okay, so if I want to do x to some power, so my general rule then, if I sort of dot this and say, well, what if you just have x to any power? Let's call it n. N is just any number. And you wanted to do the derivative. Well, again, I could use my terrible, awful formula up here. But if I'm trying to just sort of maybe make an educated guess based on the ones that I know, you know, I don't think it's unreasonable to say, well, whatever number's here, just by looking up at this little list here, kind of looks like it ends up as the coefficient of x. So sort of stare at that for a second or two, and hopefully you don't think I'm crazy, and I don't think you're crazy, if that kind of makes sense, that kind of looks like what's happening, right? I mean, it is. Okay, so we're kind of almost there, but maybe just one more thing. What else do I have in these 3 examples that I listed up here? I have some power of x. Now I'm going to do a thing that, you know, you might not love. Let me leave that circled. At 1, okay, if I'm trying to say, well, what power of x is that? Well, there aren't any, right? It was just, remember, it was just 1. So there are no powers of x. So that's technically actually okay. I could say that. Remember, anything to the 0 power is 1. So, all right, so if I look at this now, and sorry, let me also put that in there. Then I'm going to ask you to do a little bit more imagining with me here, and let me switch colors. And let's just sort of say, all right, so do I notice some other relationship? So again, I'll come through here and ask you to spot this with me. So when I had x to the first power, I ended up with x to the 0 in my answer. When I had x squared, I ended up with x to the first. And when I had x cubed, I ended up with x squared. Okay, so again, it's not a huge leap of faith, but it kind of looks like the exponent, or the power up there, doesn't it kind of look like it's 1 less than the one you started with? I think so, right? I mean, for the 3 examples we wrote down, that's true. And again, it'd be kind of a really strange coincidence if that wasn't actually always true. And in fact, it is true. Okay, so if I start with x to the nth power, I'm going to get an n in front as a coefficient, and then x, and then what is the exponent? It should just be 1 less than the one I started with. So I should subtract 1 from the exponent. And that, believe it or not, is our first shortcut. Okay, so I'll box it here for you. And in many ways, that's actually kind of maybe the most applicable one, really, of all of the rules, is that one. What else to say about this guy? Well, I've run out of space here, so let me go on to a new slide here. I'll just try to make this a little more grand for you here, right? So our first rule, our first shortcut, is for f of x equals x to some power, the derivative, which I'll always try to do as a sort of arrow like that, derivative, is the exponent times x, and then subtract 1 from the exponent. Okay, so that's our first shortcut. So this works for x to the 0 power, which is a constant. It works for x to the first power, which we already explored. That should give you 1. It works for x squared. It works for x cubed. And it works for and in fact, it works for any number you want to put up there. So as silly as it sounds, we could ask, what's the derivative of, so all of these questions are, what's the derivative of? If you wanted x to the 8th power. Now again, you could do it using the f of x plus h guy, and you'd get an answer, right? But I think we've made a pretty clever observation right here that this rule here seems to be a major time saver, because how long does it take me to use this rule? About 5 seconds, I think. And what is my probability of error is pretty low, because there isn't a whole lot I have to do. If you have x to some power, the derivative says, what should I do? Well, following this rule, it would say put the 8 in front, x, and then subtract 1 from the exponent, which would leave me with what? 7. So 8x to the 7th that's the answer, and that's correct. And look, that took me 5 seconds to do. So okay. Now this is nice. I think this is actually maybe even amazing in a lot of ways, that this now lets us do x to any power you want, x to the 40th power, x to the millionth power, whatever you want. Now, of course, these are a little bit ridiculous. I mean, nothing in the world is really modeled by x to the millionth power, because that's just sort of a nonsense concept. So, okay, this is nice, but where else does this help us? Well, actually, there's what could n be? Well, n could be these positive whole numbers like we've been talking about, and that's reasonable. But actually, n could also be fractions. So I could have, for example, something like x to the 3 halves, or x to the 1 1/2. And this rule still works. Now, it looks a little bit weird, but it works. So what would the rule say? The rule would say, if you want to do the derivative of x to any power, then you should pull the power in front. That becomes the coefficient. So 3 halves becomes the coefficient. And then x. And then I'm supposed to subtract 1 from the exponent. Well, 3 halves is 1 1/2. So if I subtract 1 from 1 1/2, that just leaves me with a half. Okay? So that would be the answer. Again, that took me about 5 seconds to do. But remember also, what's x to the 1/2? You wouldn't have to write this, but just a reminder from our pre-calc review. Remember, 1/2 power is the same thing as a square root. So really, you'd get 3 halves, or 1.5, times the square root of x. Okay, which then maybe does beg the question, so then what about the square root? Could I do the derivative of the square root of x? Aha. Well, this is now all of a sudden, I would say, I mean, the answer is going to be yes, but this is now seemingly, I don't know, extra good or extra amazing in that square root, well, you know, conceptually, that's a thing that we sort of have some understanding of, I hope. But, you know, hopefully that doesn't cause a crash. No, we're good? Okay. Square root is sort of something that's, I don't know, it's this strange character, and yet, believe it or not, this rule, this very simple rule that we've kind of discovered and, you know, accepted, actually helps us to answer this question too. So how would I answer this question? What is the derivative of the square root of x? Well, I have to use, the one thing I will say that is a negative about rules, or shortcuts, as I'm calling them, I guess, is that you have to be very careful that you use them carefully, and you only use them as for an application that they're supposed to be used for. I know that sounds sort of silly to say it that way, but what you have to do is say to yourself, well, all right, what is this derivative? Well, the shortcut that I have says if you have x to some power, here's the answer. I don't have x to some power. I have the square root of x. So please don't do the following. So it's tempting to say something like, well, x is x to the first power. And in fact, the derivative of x to the first power, we already explored that, is 1. So I could say, all right, so the derivative then, I'm going to just sort of, I don't know, carry over the square root sign. And then I'll say the derivative of x is 1. And the square root of 1 is 1. Okay, so this is where you've abused rules or abused shortcuts, because you can't say that. We don't have a rule that lets us say, what do I do when I have the square root of x to some power? I don't have a rule that says that. The only rule we have right now is this one that says if you have x to some power, here's a fast way of getting the answer. Well, I don't have x to some power yet. I have the square root of x to some power. So I can't do that. But what can I do is I can say, but wait a minute. I know that the square root of x is actually the same thing as x to the 1/2 power. Now that's a fact. Now I didn't do a derivative or anything yet. That's just a rewrite. That's just like instead of saying 2/4, you can say that's the same thing as 1/2. It's just a rewrite. So square root of x is literally the same thing as just x to the 1/2. Aha. But now, this exactly, x to the 1/2, that looks exactly like our rule. Our rule says x to some power, and here's how you do the derivative. Now I have it. It's written as x to some power. Now I can use the rule. Okay? So now I can use this shortcut and say, all right, if you have x to some power, the derivative is given by, you bring the power down in front, so it's 1/2, so n is 1/2, so that's 1/2, x, and then I subtract 1 from the exponent. So it was 1/2 to begin with, and I have to subtract 1, that's negative 1/2. Okay? Or, again, you don't have to simplify this, but if you wanted to, remember, negative powers, negative exponents, are the same thing as the positive versions on the bottom, or in other words, move it. So right now, this is x to the negative 1/2. X to the negative 1/2 is on the top of this fraction, or it's sort of on the side, I guess, but the side is the same thing as saying it's on the top. It's multiplied. So if I wanted to, I could actually say that this is the same thing as, if I want to put that on the bottom, I could, and then it would become x to the positive 1/2 if I move it to the bottom of the fraction. But x to the positive 1/2, remember, is just the square root. Okay, so we've sort of gone a long way around here, but the square root has a derivative 1 over the square root of x. That's the derivative of the square root of x. Okay? Now you don't need to memorize that, right? You could just use the rule. So the only thing you have to remember is that you have to rewrite. Okay? But don't tell me that the answer to the derivative of square root of x is x to the 1/2. It isn't. That's just a rewrite. You didn't do anything yet. Okay? But rewriting it as x to the 1/2 makes it look exactly like our rule up here, which means I can now use the rule. But again, just be careful here. You can't just kind of willy-nilly use rules. You have to actually have the rule sort of satisfied. In other words, you have to make it look like the left side of the rule. Otherwise, if you use it, you're probably not doing so correctly. Okay? But this brings up one more point then, which is that I can then do negative exponents. Remember, the other type of exponent we might have, I could have whole numbers like 8, or I could have fractions like 3/2 or 1/2. But the other type of exponent that I might have would be negative numbers. So for example, I think if I have f of x equals 1 over x squared, I think I actually know how to do the derivative of this. But again, word of caution, all right? Don't do the following. I should probably not keep doing the wrong ways, but I'll do it anyway just to show you what not to do here. So it's tempting. It's very tempting to say, oh, well, I know that the derivative of x squared is 2x. We've done that one a whole bunch of times. But even this rule, right, the derivative rule here would say if you have x squared, that would turn into 2x to the first. So yes, that's true. It's true that the derivative of x squared is 2x. That's true. So it's tempting to say, oh, all right, so I know that the derivative of 1 over x squared, oh, well, that should be 1 over 2x, because the derivative of x squared is 2x. So there, I did it. Okay, that's wrong. And you say, oh, okay, well, I got it. Okay. So the derivative of 1 over x squared, well, the derivative of 1, remember 1 is a constant, and we said a few minutes ago that the derivative of a constant should be 0. Oh, okay. So the derivative of 1 is 0, and the derivative of x squared is 2x. Oh, okay. 0 divided by anything is 0. So 0 is my answer. That's wrong too. Okay, so I've hopefully not given you bad ideas by doing this problem wrong twice. But I just wanted to say that I know it's kind of tempting to think, well, all right, I see something here, or I see something I can do, and just be careful. When you're doing shortcuts, the only thing that's bad is that shortcuts, as a general rule, just in science in general, means that you're going to sort of bypass some steps and just say, cut to the chase, and here's my answer. And that's fine, but you have to be very careful when you use them. You can only do what the rule says you can do. You can't use it on things that are kind of like the rule. No, you can't do it. All right? So let me erase all of this wrong stuff first. And instead say, all right, well, okay, let's try again then. So all I have is this rule that says it's x to some power, any number you want up here, n, then I could do it. Well, this doesn't look like x to some power. This looks like 1 over x to some power. So I can't do it. But just like I could do in the previous example with the square root, I think I can do a rewrite. Because I know that when I have exponents on the bottom of a fraction, I can flip them to the top of the fraction by changing the sign. So in other words, instead of 1 over x squared, I could put the x squared on top and make it negative. In other words, or I should say make the exponent negative. So x to the negative 2 is the same thing as 1 over x squared. Now again, I haven't done anything yet. That's just a rewrite. But now this looks exactly like my rule because it's x to some power. Aha, okay. I have now passed the test to say, yes, the thing I'm looking at looks just like that, so I can use the shortcut to say, so that's my answer. Okay? So now is an appropriate time to use the shortcut and say, so the derivative becomes, well, let's see, so negative 2, that becomes the coefficient. and then x, and then I should subtract 1 from the exponent. Well, that would bring me all the way down. That would bring me down to -3, right? -2 minus 1 is -3. Okay, and again, you don't have to rewrite this, but if you wanted to, you could say that's -2, and then x to the -3 is really the same thing as x to the +3, but on the bottom. You don't have to rewrite that, but in case you wanted to, that would be the same thing. Okay, so this is actually a pretty good rule in that this lets you now do any exponent, x to any power, positive, negative, fractions, square roots, cube roots, all of these characters, you could now do the derivative of just by using this rule. It's a very, very good and very helpful, and then, like I said before, it's probably the most basic and most applicable rule out there. So this is the shortcut. Sometimes this is called the power rule or the power formula, I guess, or something. But okay, whatever. This is it here. So what other shortcuts do we have? So this is sort of one. I'll make a little chart of this on the next slide. That's sort of the main guy. And again, it takes the form of, that tells you what the derivative of a constant is, although sometimes you might write that separately just to remind yourself that the derivative of a constant is 0. That tells you what the derivative of just plain old x, just x to the first power, because you could do n equals 1, and that would tell you about x. And it tells you x squared and x cubed, and then also x to any number you want. That's how you do the derivative quickly, right? I mean, no matter what situation you're in, this takes at most a minute. Even with these rewrites down here at the bottom, it still only takes about a minute to do. So that seems to be a good rule to help us deal with polynomials. So, you know, x cubed and x to the 4th and all those guys. This seems like this is our friend. This is our rule for that. But how about our other characters, our other functions? Well, we know there's more than just powers of x. We spent the whole several lectures reminding ourselves of how to do exponential functions and logs and trig and all that good stuff. So there must be, or well, I guess one would hope that there are maybe derivative shortcuts like this one that we just derived, that also that you could use for trig functions and and logs and all that. And there are, and that's what I'm going to present or put on the next slide here. Okay, so so who else? So now I'm not going to say much at all about these characters in terms of trying to derive them for you. They do all come from the f of x plus h blah 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 thing. But maybe don't write any of this down in your notes. I'm just going to erase this as soon as I write it down. But let's say I wanted to say, what's the derivative of, something like sine of x? Well, all right. I don't really have any rule right now that would work here, right? The only rule or the only shortcut we have deals with powers of x. Well, sine of x is not x to some power. It just isn't. It's sort of a whole new character. So I'd have to say, well, I don't know what that is, but I guess if I wanted to do the derivative, I'd have to use the definition of the derivative, the f of x plus h guy. So I'd say, all right, well, it's f of x plus h minus f of x over h. Ugh. What the hell am I supposed to do with that? I mean, that's a disaster. I don't really know. I mean, you guys know. I mean, I know you're not trig experts, but you know that trig is sort of a strange character to begin with. So how do I even go about trying to put that together with that? And the answer is don't. The answer is stop right now, because this does not combine very nicely. Now, are there super fancy math ways of trying to sort of put this together in a meaningful way? Yes. And, does it involve some kind of actually rather complicated math? Yes. So one can do this. I'll just say, smart math person. Okay, I'll be honest. I don't know that I could actually do this. But anyway, one can try to do this the long way, and one will eventually come about and say, oh, I did a bunch of steps, and I secluded myself in my bedroom for a month, and I figured out, oh, okay, the derivative is blah. Via canceling and whatever, all this other stuff. Okay, so one can, right, do the derivative the long way for all of our family of other types of functions. And if one does, and if one really did all of them out, there would be no need to ever do them again, right? I mean, if you did this once and you actually did, you were a smart person who did this, you'd never need to do it again, because the derivative of sine of x would always be whatever you got here, right? I mean, you wouldn't need to redo this every time you'd encounter it. So it's perfectly good for us to just say, well, all right, some smart people sat down and they did all these derivatives and it took them forever, but they did them and here they are. Okay? So, and that's more than good enough for us. I mean, there is no need to go and do these all out by hand or anything like that. So I'm going to go ahead and just put an X through that whole thing and say, let's take advantage of what smart math person did, and let me just present them all to you here. And here I'll make a chart for you. All right. So this is sort of a good thing to have. So you may even want to write this on a separate piece of paper, like a blank sheet of paper or something, just to have, kind of at your easy access. You might just sort of keep this on a spare sheet because you're going to use this all the time to do derivatives quickly. And we're going to add to this. So, but if you just do one blank sheet of paper, you can get it all in there probably. So, so this is our derivative chart. Okay, so on the one hand, we're going to have a function. And then over here, I'm going to tell you what's the derivative. Okay? So a function on the left, derivative on the right. What else are we going to put on this chart eventually are going to be some rules. So either leave yourself some space under this little chart, or even actually off to the side is, I think, how I usually do it. We're going to have, I think, it'll end up being 5 rules that we're going to use. These are shortcuts which we're about to fill in, but we're going to have 5 rules. This will take us several more lectures to do these 5. So anyway, don't worry about that right now. But what are the basic building block shortcuts? All right, so what is it we've done so far? Let me just fill in the ones we already did. So we already said if you want the derivative of a constant, which again is just some number like 5 or -3/2 or whatever number you want, we decided that the derivative of that is 0. If you want to know what's the derivative of just plain old x, we decided that the answer to that is 1. And our most recent discovery, which is wonderful, is that if you have x to some power, the derivative of that is n, that power, times x, and then subtract 1 from the exponent. Okay, that's the sum total of our chart so far. We know those 3 things. Well, who else is here, right? Who else is missing? Well, somebody who's missing would be E and ln. So remember when we did our review, we sort of said, well, we're going to have a need to maybe do the exponential function, which is e to the x, and maybe we're going to have the need to do logs. And we said, well, the only log that we actually really going to use is the ln of x, the natural log. So these are 2 important players and characters in our calculus story here. So we should know what the derivatives of those are. All right, and again, here's where super smart math person sat down with that clunky formula and computed these 2 derivatives for us. And we're just going to take advantage of the fact that they did that already and use their work and say, here's the answer. So e to the x, the derivative of e to the x, if you did it out the long way, you'd actually find is e to the x. So it's sort of the very funny, funky character. We'll talk a little bit more later about why that works out. But the derivative of e to the x is actually just e to the x. So that's our favorite derivative because it's so easy to remember. It's just itself. Okay, the derivative of ln of x turns out to be 1 over x. So I'll sort of draw it that way, right? So 1 divided by x, or 1 over x, or x to the negative 1 if you'd like. Okay, so there's those guys. So if we want to know the derivative of ln of x or e to the x, there's our answers right there. All right, and then who else is missing? Trig. Trig is missing. So cosine and sine and tangent, those are our 3 main trig functions. But while we're here, I'll give you the other 3 anyway. We have cotangent and secant and cosecant. Okay, so those are our 6 trig functions, and this is the end of the chart, right? So these, what do we have, 6, 7, 8, 9, 10, 11, I guess, rows. That's our whole chart. All right, we're going to, like I said before, we're going to do some derivative rules over here on the right, but we'll do those next time. But here are the 6 trig functions, and here are their derivatives. And again, this came about by somebody doing this the long way. But here's what that person got when they did the derivatives. Cosine, the derivative of cosine turns out to be negative sine of x. The derivative of sine turns out to be cosine. Okay. I'll say more about these. Let me write them all down first. The derivative of tangent turns out to be secant squared. Okay. The derivative of cotangent turns out to be negative cosecant squared. The derivative of secant turns out to be secant x times tangent x. And the derivative of cosecant turns out to be negative cosecant of x times cotangent of x. Okay, so let me just say a little bit about the trig stuff at the bottom there then. So, there's lots of things to, observe, I guess, none of which are all that important. But, sine and cosine, they kind of are buddies, they're sort of cousins. And so it's kind of reasonable that the derivatives of sine and cosine are just sine and cosine, more or less. So, that's maybe not the most surprising thing that those would be similar. Tangent and cotangent are also kind of very similar to each other. And so again, you kind of look at the derivatives and they're also quite similar. And then same story for secant and cosecant. The other thing you can notice is that all of the cos have negatives in the answer, and all of the, not co don't have negatives. So I don't know, there's a variety of things that you could at least just notice, I suppose, but it's not that important. You're going to have this chart and refer to this chart whenever you need to do any derivative. So this is it. Like I said, these are our sort of 11-ish building block, I guess I might say, derivatives. And so whenever we want to know the derivative of anybody, we can just come right to this chart and look it up. And that really does save us from having to do an awful lot of algebra and just nasty stuff. All right, so I guess that's it for here. I would say I would do examples, but I don't, so the example, if f of x is ln of x, then the derivative is 1 over x. There's not much to say, right? That's the whole point of these shortcuts, is that they answer the question, immediately for you. If you wanted to do the tangent line, I guess, right, you could then say, oh, okay, well, if you know the derivative, you could plug in an x value and get the slope. So, I guess there's something to be said there, but that's pretty, the chart itself is really where it's at. And knowing these derivatives is tremendously helpful in terms of cutting down having to use that awful formula. So, and again, any of these guys. Now, maybe I'll just leave you with the thought, if I wanted to say what's the derivative of maybe x times ln of x, right? Or x times ln of x. Well, it's tempting to say, well, I know the derivative of x. That's in my chart. It's 1. And I know the derivative of ln, that's in my chart. It's 1 over x. So x times ln of x, the derivative, guess should just be that, right? 1 times ln, 1 times 1 over x, which would just be 1 over x. And that would be sort of nice, but you can probably tell by maybe the tone of my voice, that's wrong. So again, slapping us right in the face just when we were maybe thinking calculus was not the devil, is something like this, where we say, oh, I was pretty happy with this chart that we just drew here, because it kind of it seemed like my life was going to be not that bad, and it isn't. But the moral of this story and preview of what's to come in the next video is that these building block guys here, as I'm calling them, it's nice to know what those derivatives are, but that's not going to be the only thing we need to know in order to do derivatives. We're going to have to know something like, how do I legally, let me erase my x here, how do I legally say, well, if you have one guy that you know about and another guy you know about, and you multiply them, how do I do the derivative of that? And this is not correct. That's not the right answer. But there will be a way to do that. And that's what we need these extra, as I mentioned before. We're going to have, I guess, what turns out to be maybe 5 sort of derivative rules that are going to let us address these other sorts of questions. Okay? So that's what's to come in the next video, is how do I put these building block pieces together to be able to do more complicated derivatives. And believe it or not, that's kind of the end of the derivative story once we know those rules. Now, those rules are going to take us a few videos at least to be happy with. But that's actually kind of the end of the how to do derivatives. So the rest of this course is all about why do I care and what would I use them for. So, okay, so check out homework problems that will be appearing shortly for just some basic practice with this. But for the most part, the most interesting problems are the ones that will use these rules, which we'll do in the next video.